let me say the following. You are permitted to fit models which have the same degree of, if you will, human error that you run into when you try to repeat a performance when all the circumstances surrounding the experiment are held constant. And so in a sense, your models permitted the same sort of license, the same sort of looseness, the same sort of error that you run in when you run in and repeat an experiment. So actually a sort of a rough rule of thumb we often run into is to say, well, don't really get terribly disturbed about your lack of fit test unless the F ratio is perhaps as great as twice the critical value of F. So I guess what I'm telling you is the following, that although technically we've shown that our second order model is inadequate to represent the data, I would rather take the view that, well, it's uncomfortable. It's not as good as I might do, but, you know, I wouldn't really throw it out. I wouldn't purge it from my mind, you see. Let's toss it out anyway. Let's say that we could have done a better job of fitting that data had we tried some transformations in X and Y. We probably never would have gotten to a second order model. Or even with a second order model, our interest would be, of course, in getting the second order model to fit, possibly by making transformations. Well, this brings us to what would we do next if we threw out this second order model? Somebody would say, fit a third order model, Stu. Try these, you know, what the heck, try another polynomial approximation to the unknown response function. And you, of course, could do that. You could try a third order model. You've just got through fitting a second order model. Gee whiz, why not try a third order model, a third order Taylor series approximation to the unknown response function? Well, that would require you to put on a cubic term in your mathematical model. Right? You know what my attitude towards that is? Scorn, scorn. I just don't like that idea at all. We're trying to get approximating polynomial models that are useful, approximating polynomial models from which we can learn. Now, do you really think that the unknown response function is cubic? Do you think it goes up and has a bump in it? Do you feel that deep in your breast? If you do, be my guest and fit a third order model. But if you don't, right, there's no real sense in fitting a third order model. It's a bit of mathematical gingerbread, if you will. You could fit a fourth order model to these data if you wished. It'd be not a good idea, because if you were to do that, you would be just getting a large interpolation formula, which would only be appropriate for this special collection of data and would not be appropriate from another collection of data that you might try another time. You wouldn't learn anything from the model. It would be like, you know, interpolating in a mathematical table, trying to find reasonable values between the observed values and so forth. And that's not enough if you're trying to learn something from your data. So my attitude towards third order models is no siree. On very rare occasions would I ever fit a third order model. Much more important to you is to get the proper transformations to produce a simple model. Don't be afraid to make transformations in the x-axis or transformations in the y-axis to get it to be a straight line if possible. When would you fit a second order model? You only fit a second order model when the function peaks and comes back down again over the experimental region, or perhaps comes down and goes back up again. Then you have to fit a second order model. But if your curvature is of a sense that it asymptotes, or if it's just slightly curved, then don't even fit a second order model, because invariably you can find a transformation, use your rubber graph paper to straighten that blooming thing out.